This video is about genetic pedigrees and how they can be used to show the passing on of traits through multiple generations. This introduction is to help you make your own genetic pedigree eventually for your Level 4 project. So the genetic pedigree that you see here is this kind of structure. Okay. Each of these boxes and circles represents people, and each of these levels represents generations. So I'd like to just take you through some of the symbols so that you can see how this works. So I'm going to make this little box up here a little bit bigger here first. Okay. So as you can see in this box, all of the squares in the pedigree represent males, and all of the circles represent females. If the squares or circles are shaded in, that means those individuals have a trait that you are actually looking for. So in this case, they don't say what the trait is, but whatever that trait is, the ones that are shaded have the trait. If a circle and a square are connected, that means that they have mated, they have had children. I know it sounds a little weird to talk about people mating, but people aren't always married when they have children. So in a pedigree, it's specific to individuals that have had children together, whether or not they are married. In order to show those children, in this next little key, it shows how there is a vertical line that comes down from the parents, and then a new horizontal line to connect all their children. And you'll notice that the generations have changed. We've gone from generation 1 to generation 2 to show that we've got children coming in. The birth order is specific here. So the child that's the furthest to the left, so this one was born first, and the child that's furthest to the right was born second. If a family would have identical twins in it, that connection between parents and children would look like this, and then connecting the children together as well. If they're non-identical twins, it just has that forking connection. All right, so that gives you kind of an idea of what the symbols are. So let's read some of the examples from this pedigree that I shared with you. So what we have going on here in generation 1 is a man and a woman have 1, 2, 3 children. 2 of those children are girls, and 1 of those children is a boy. Each of their children then has children with other people, so you can see them mating, connecting them to other people. Notice these other people are not connected up above to the first generation. So for example, this person right here is kind of free floating, only connected to the woman. And when they have children in this first couple, they have 2 children, 1 girl and 1 boy, and the boy has the trait that his grandfather had back in generation 1. Some other connections, family connections. If we take a look at this girl down here, this individual, number 2-1, so Roman numeral 2 means generation 2. Cardinal or the number 1 equals this first person. That would be an uncle to individual 3-3. Individual 3-3 and individual 3-5 would be cousins. So hopefully that makes a little bit more sense to read that genetic pedigree and to see kind of what all those familial connections actually are. Now, the next thing we can do with a pedigree is we can figure out what type of trait that family is passing along. So if I made this tree for all of my family members, and I was tracing something like blue eyes, let's say. So these boxes are already blue, so we're going to say anything that's shaded blue is blue eyes. And anything that's unshaded is another color. Could be brown, could be green, something else. So the ones that are shaded blue have the trait of blue eyes. Now you can use a pedigree to figure out, is that blue-eyed trait dominant or recessive? And here's the key to figuring that out. You need to look for a set of parents that has a child different than themselves. So right here, these parents have a child that's different from them. They do not have the trait, their son does. That tells us right away that the parents have to be heterozygous. For example, they have to be big B, little b, and big B, little b. Because the only way they could look different from their sons and still pass on that different trait is if they were each hiding a little b allele to make their son homozygous recessive. So the parents are dominant, the child is recessive, but they have to be heterozygous in being dominant because they passed on that little b allele to their children. So if we go through and do the entire genotypes then, after we know that it's a recessive trait, that helps us to figure out what some of the other individuals are. So I'm going to put these back in. Got little b, two heterozygous parents. Okay, that means that all the shaded individuals now have to be recessive because it's a recessive trait. So this one is little b as well. Now this dad had to pass at least one of his little b's onto all of his children because that's how meiosis works. So we're going to put a little b with all of his children. And we know that those children who have the little b must also have a big B because they do not have blue eyes, so they must have the dominant trait. The rest of these individuals, for example, this mother up here, we know she has the dominant trait, so she must have a big B, but we don't know if she's hiding a little b or not. If you look at all of her children, there are no children that are homozygous recessive, so we don't know if she's hiding a little b or not. So to show that, we just put a slash. What that means is she could be big B, or she could be big B, little b. We don't have enough information to know. Let's look at this individual here, 2, 4. This woman has to have a big B because she does not have the trait. Does she have a parent or children that are recessive? No, not that we know of, so she is also a blank. Individual 2, 6 must have a big B. Does he have a parent or children that have the trait that's recessive? No, so he's also a blank. And you're going to see that over and over again in this particular pedigree. We don't have any other homozygous recessive individuals that can give us a clue to the genotypes of the others. So all of these other unshaded shapes, we don't know the actual genotype of. The only one we know for sure, again, is individual 2, 2, because she has a parent, if you follow the line up, that's little b, homozygous recessive, and she has a child, that's little b, homozygous recessive. So again, this is a recessive trait because we have parents who have offspring that look different than they do, and then you can use the fact that it's a recessive trait to fill in as many other genotypes as possible. So now let's take a look at this pedigree and see if we can figure out if it's another recessive trait or if in this case it might be a dominant trait. Again, look for the key. Are there parents that have children that look different from them? So this first generation up here, okay, has a parent of each type, and they have children of each type, right? Here in generation 2, child 1, individual number 3, individual number 5, individual number 6, individual 8 are all children, but they look like the parents because the parents both have the trait and don't have the trait. So we don't know if it's recessive based on that. Now let's keep looking down a generation. of this couple, one of each, so that doesn't help us, right, because their children look the same. This couple, we have two people without the trait, but all of their children are without the trait as well. So that doesn't help us, no difference there. And this couple over here, again, they each have a different trait, and all their children, kind of have that different pattern too. So again, it's no different from the parents. So we don't have an example of two parents whose phenotype is different from their offspring. So if you don't have an example of that, you're going to assume that your pedigree is a dominant trait. So that means all the individuals that are shaded, okay, that have the shading, are going to be dominant. And that means that they're going to be big B, or big B, little b for their genotype. All the unshaded are going to be recessive, which means they're going to be little b for their trait. All right, so let's go ahead and fill in what we can on this pedigree. All right, the first thing you want to do is find all those unshaded ones. Remember, the unshaded ones are recessive this time, and fill those in because that's pretty easy. I'm going to do those little b's again inside all of the unshaded shapes. So these are all recessive ones. Remember, we determined this is a dominant trait, so all the shaded ones with the dominant have to have at least one big allele, which means all the unshaded ones are going to be recessive. All right, so let's go ahead and put that one dominant allele in each of the shadeds, because we know they have to be at least one to be big B, or big B, little b. And then from there, let's see if we can figure out if there's a little b hiding with any of those dominant individuals. How do we do that? Again, we look to see if they have a parent or a child that's little b, because that means that they either got it from their parent or they had to give it to their child. So for this individual here, he has children that are little b. The only way his children could have been little b is if he gave them one of their little b's. So he has to be heterozygous. If we look at individual 2-1 right here, he has a mother that was little b. So he had to get a little b from her, and to double check, he also has a child that was little b. He had to give a little b to that child. Let's keep going in generation 2, individual 5 right here. She had a mother that was little b, had to get a little b from her. Generation 2, individual 8. This one had the mother again, that was little b, has to be getting that from her. Down to generation 3. This girl has a mother that's little b, she had to get that allele. This boy has a father that was little b, so he had to get that allele. And this girl also had a father that was little b to get the allele. So in this particular pedigree, we're able to fill out every single individual in their complete genotype because all of these recessive ones help us to see what's being hidden.